and that is 24.5 degrees. Okay, so now we've determined one angle. We now have to go and pick our second spot along the beach.
The distance from the first to the second point must be measured accurately. In this case it's 100 meters, and the 2 points must be in a straight line with the mountain. I measured the second angle to be about 26.5 degrees, and now had enough information to calculate the height of the mountain. Using trigonometry and algebra, Al-Biruni used a formula that relates the height of the mountain to what are known as the tangents of the angles he measured. Using my measurements, I get a figure for this mountain of about 530 meters. I now need only one more measurement to get the size of the Earth. And to get that, I have to climb to the top of the mountain.
What Biruni did next was measure the angle of the line of sight to the horizon as it dips below the horizontal. So we're going to try and reproduce that. So if you can lift it up so that it's hanging, and if I locate the horizon, okay, which is about 0.5 degree, which is about the value that Biruni got. Now here's the really ingenious part. Biruni had measured 4 quantities, 3 angles and a distance. He used 2 of the angles and the distance to work out the height of the mountain.
Al-Biruni now had everything he needed. In essence, Al-Biruni imagined a huge right-angled triangle which has as its 3 corners the mountaintop, the horizon and the center of the Earth. Trigonometry told him that the angle he had measured and the height of the mountain are related to the radius of the Earth, and algebra allowed him to calculate it.
With this formula, Biruni is able to arrive at a value for the circumference of the Earth that's within 200 miles of the exact value we know it to be today, about 25,000 miles. That's to within an accuracy of less than 1%, a remarkable achievement for someone 1,000 years ago. For me, Biruni's experiment is an early dramatic example of a scientist using mathematical reasoning to extend humanity's reach. He really pushes the idea that abstract geometrical rules governing idealized shapes like perfect circles and triangles can help us to comprehend the real world. Einstein used precisely the same approach, admittedly with much more advanced mathematics, when he developed his general theory of relativity almost 1,000 years after Biruni. But both Einstein and Biruni were united by a single common idea. With mathematics, humanity can embrace the universe.
In this story of the birth of the scientific method, the Islamic scholar's ability to master sophisticated mathematics is the first crucial ingredient.
The second crucial ingredient is the use of experiments in science. Without experiments, theory remains meaningless and sterile. It's experimentation that allows theory to be held up against the real world. It gives it physical meaning. But whereas sophisticated mathematics grew out of the empire's obsession with the world's learning through the translation movement, practical experiments came from the daily needs of a powerful and expanding civilization.
The driving force of the expanding medieval Islamic empire was trade. It boomed from around 700 AD onwards, creating a massive demand for metal workers, glass blowers, tile makers, craftsmen of every possible kind. When this collided with scholarly tradition, symbolized by the translation movement, it had seismic consequences for science.
The sciences absolutely depend, astronomy is a wonderful example, chemistry is another, on really intense relationships between craft traditions of instrument making, of working with metal and fire, of working with medicines, drugs, plants, and scholarship, highly sophisticated literary and mathematical analysis. And the Islamic world is just such a place.
By around 800 AD, the great cities of the Islamic Empire dominated the world's trade. To its markets came silks, spices, drugs, fruit, perfumes and gold, from as far afield as India and China in the east and Spain in the west. Anything that could be traded was. A wonderful relic of this medieval trade boom are the great caravanserais, like this one in the Syrian capital, Damascus. This huge vaulted building was designed as a resting place for all the traders and their animals who visited the city. On their ground floors were wide spaces for animals and goods. And above there were rooms for the rich merchants to refresh themselves before another day of haggling. One 10th century traveller talks of the riches and beauties of the bazaars, and that the income of the provinces and localities was between 700 and 800 million dinars. Markets like this in the Egyptian capital Cairo still capture the intensity of medieval trade. And still surviving in the modern world of the internet and the mobile phone is a fantastic example of how traders 1,000 years ago communicated across a vast empire.
So this is a carrier pigeon, its base is here, so wherever you took this pigeon all over Egypt, it will make its way back to this guy. There's a famous story that a rich Cairo merchant by the name of Onur wanted to grow cherry trees, so he sent a message with a carrier pigeon to a contact of his in Damascus asking for some seeds. His contact sent back 500 birds, each one carrying a small bag with seeds in it. The whole process took just 3 days. Sort of a medieval FedEx, really.
By 700 AD, the Islamic Empire was taking the first steps towards mass production. And in this world where knowledge of materials, metals, and how they're worked became increasingly important, one practice flourished. It's the practice that was inextricably linked with magic. Specifically, the dream to turn base metals into gold. The mysterious practice of alchemy.
The ancient art of alchemy was a mystical system of belief based on spells, symbols, and magic. But I believe it took Islamic scholars to turn this quasi-religion into something much more scientific. Chemistry.